Okay, hello everybody. My name is Ed. I'm going to talk to you guys about electrical engineering, and I'm also going to talk to you guys a little bit about biomedical engineering because I'm both an electronic engineer and a bioengineer. So I'll just give you a quick bit of background to myself about how I got to where I am today. How does this work? Okay. I'm from Dublin. I did my Leaving Cert in Rathfarnham. That's where I went to school. I went to the NME, UCD, to do electronic engineering. After that, I went to the States. I went to Los Angeles for a year and a half to study a master's degree. Came back to Dublin, worked as a silicon chip designer for a little while. Decided that wasn't for me in the long term. So I went and was lucky enough. Do you guys know MIT from the Massachusetts Institute of Technology? Set up a lab in Dublin a few years ago, and I was lucky enough to get a job there where I did some research that I'll talk to you a little bit about, kind of engineering research that I did, and that led to a PhD, a doctorate in electronic and biomedical engineering from UCD a few years ago. That gave me the opportunity to go to the States to do more research in New York, where I lived for a couple of years, came back to Trinity College, spent a little bit of time in London doing more research, and started work as an assistant professor here this year. So I'll briefly talk to you about electronic and electrical engineering in general, and then again I'll go into a bit more specific detail about Trinity College in particular, and then finish off with some examples of kind of what an electronic/biomedical engineer might do. So electronic engineering is everywhere. It's all around us. Every one of us that has a mobile phone or a smartphone or a laptop or whatever are involved. You know, we're able to use these things as a result of the efforts of electronic engineers. People who look on the internet, engineers have had a part to play in that. You know, even cars, there's electronic chips in cars nowadays. There's electronics pretty much everywhere, and they're not going away anytime soon. So the demand for electronic engineering is not going to go away. And in fact, the kind of cool future gadgets that people will have in their pockets or in their bodies or whatever will likely be made by electronic engineers that have a lot of input on that. So there's some specific kind of subsections of electronic engineering that people might get into. One, for example, is telecommunications, satellite transmissions, mobile phones, smartphones, digital television, computers, obviously. And this is an important point to make. Most of you guys may know this already, but one of the things that the electronic engineering department in Trinity do is they offer not just pure kind of electronic engineering, but they also offer the opportunity to do some computer engineering, or a mix between electronic and computer engineering. So that's an option that some people find attractive. Also then there's, in the more kind of pure electronics domain, there's the idea of microelectronics. As I said myself, I worked briefly as a silicon chip designer. It's challenging work, and again, all of our technology and devices that we have now wouldn't exist were it not for people who were working on these kind of microelectronic devices. Power systems and so on, this is more electrical engineering, I would suggest. Again, this is a hugely important area going forward. You know, there's going to be an energy crisis. I mean, it's a fact. We're going to run out of oil. We're going to have some other way of powering what it is that we do in the world, the standards of living that we've gotten used to. So, wind turbines and stuff. There's a big PhD program going on at the moment. There's about 10 new PhD students all working on research towards coming up with new ways of producing energy for us. Things like electrical machines, robots, electric cars, again, going to be something of the future. And electronic and electrical engineers are going to have a major role to play in future society. I'll talk a bit more about biomedical engineering as I move on, because it's my own particular area of interest. So I'll just kind of skip over this right now, just to say that, I'll talk a bit more about it in a while. Okay. Attributes of an engineer. So I was always told, what is engineering? Well, engineers are people who basically like to solve problems. So they're people who are interested in science and mathematics, because at the end of the day, to describe how a piece of technology works, the language that you use to describe that is mathematics. If you can't work through some mathematical equations to show how a piece of equipment or a piece of technology might work, then you won't be able to actually do anything with that piece of equipment. But it's not just about understanding the science. It's about actually taking what we know from science and applying it to solve problems that exist in the world. So what do we know about energy generation, and how can we actually make a better generator of electricity to help us in the future? What do we know about communications into space, and how can we harness that to make smartphones that work faster or better than the one I have, which is a pain in the neck. Anyway, we also need the ability to think logically, and an important aspect of engineering that's often overlooked is that it's quite a creative job. I mean, at the outset, there's the foundations of engineering that you need to kind of master, and that's a lot of kind of mathematics and scientific kind of logical thinking. But once you've actually got some skills to deploy, and you have a challenging problem that you need to address, there's a really great opportunity for some creativity to come into how best to solve this problem. Most real-life problems have many, many different solutions, and how to kind of creatively come up with the most elegant or efficient solution is a real bit of job satisfaction that comes with engineering when you actually stand back and say, wow, we really got that thing to work, and we did it in a really nice, creative way. It's got that creative angle. It's important to be able to communicate your ideas to people. I mean, if you have some great new idea for solving Ireland's energy issues in the future, and you want to go and pitch that to some politician, well, you don't want to start showing them a list of equations of how efficient this thing is going to be, because politicians, as we've seen recently with the kind of financial muck-up in the country, they're not very good with numbers, and missing €3 billion in a tax review recently is an example of that. So to be able to communicate your ideas in some kind of logical way and sensible way to help people see the big picture when you're dealing with kind of technological and complex things is an important attribute of an engineer. So engineers, if you're thinking of doing engineering, it suits a person who's curious about how things work, how the world works, how we can make it work better, what we can do. Somebody who's willing to put in some time and effort to actually understand these problems, because technological future problems are complicated things. So you want to have the motivation to try and understand how something works before you're actually going to be able to improve it. Again, like I said a minute ago, it's a creative career choice, because you get the opportunity to solve problems, and it's down to you as to how you will do that. So there's a creative aspect, and then some kind of more, well, innovation is just a kind of a buzzword really for what engineers have been doing a long time. Everything these days has to have innovation in the title, it seems. But coming up with clever, new, innovative, insightful solutions to problems is an important aspect of engineering. And entrepreneurship is a big thing too. I've had the fortune a few years ago, when I was working as part of that MIT lab, to host the two founders of Google for an afternoon, who are pretty amazing examples of technology turned into entrepreneurship. So these guys, I think they're only a few years older than I am, but they're already worth, I think, $17 billion each or something. I think that's what Forbes magazine told me the other day. Anyway, the idea, Ireland, we've been talking about the smart economy for a long time, and how are we going to lift ourselves out of recession and stuff like that. And engineers have a really, really important role to play in this, because if we're going to drive the economy forward by coming up with technological, innovations and new companies that are going to employ people and create the next Google or the next whatever it might be, kind of having an entrepreneurial slant to your work, working as an engineer, but with an eye on actually, making some solution that's going to make some money and create some jobs is an important feature. So I'll talk a little bit more about engineering within Trinity and electronic engineering and biomedical engineering specifically. So there's a lot of emphasis in Trinity on engineering innovation, so coming up with innovative solutions for issues, and creative designing. So again, I go back to this idea of creativity as an engineer. It's not just about crunching numbers through equations, etc. So Trinity, just a few bullet points about Trinity in general. It's old, right? 1592. It's been recognized as the #1 ranked university in Ireland for quite a while. Some of these numbers are a little out of date. I think we've dropped a little from the 43rd in the world, partly because of recession and funding issues, etc. But we're still ranked #1 in Ireland, and we're still doing very well in Europe. We've got a considerable amount of research funding, which allows us to operate at the frontier of research in various fields, which I can talk to you a bit more about my own work and how we're doing some of that kind of stuff. And the School of Engineering in Trinity is the oldest school of engineering in Ireland, and as such it has a long history and a well-established engineering program. So what might an engineer do? Some of the things that we're interested in Trinity, and some of the things that we would put forward in our mission, are solving issues in health, and that's something that I'm interested in particularly, is biomedical engineering, and I'll talk to you again more about that. Energy and the environment, I think I kind of mentioned already. We have a large program, both civil, mechanical and electronic engineering, working towards future energy issues. This could be electrical engineering, for example, more efficient power systems to power our electricity network. It could be within the home. I mean, the future of devices in the home is going to be radically different from what it is now. You'll have washing machines that have smart chips in them that will only run when the electricity happens to be cheapest at that moment in time, based on how windy it is outside or whatever. And we'll have all these kind of smart technology within the home and in the grid in general, that kind of thing. So engineers are going to be instrumental in that. And then, like I say, the economy, the future of certainly of the Irish economy depends on us producing some good quality engineers who are going to come up with some clever new ideas. So if you were to come to Trinity to do it, what do we offer in Trinity College specifically in terms of electronic and electrical engineering? Well, one important aspect that we offer is a common first and second year. So you guys probably know this already, but maybe you don't. So the idea is that in the first and second year you would do kind of fundamental stuff that's important for all kinds of engineering. So you do some mathematics, some physics. You get some exposure to electronics, some exposure to mechanical engineering, some exposure to civil or structural engineering, environmental issues, things like that. So by the end of your second year, you've got a lot of great fundamentals and a strong foundation from which to launch into a new kind of specialized thing. And you'll also buy you 2 years to kind of make up your mind as to which one of these things you prefer. You'll have projects, smaller projects in first and second year, design projects that will give you a flavor of the different types of engineering. So some of the projects involve a bit of electronics and a bit of mechanics. And so, for example, so that'll give you a flavor of which of those two kind of types of work you like. And then after that, then you specialize in third, fourth, and now fifth year. So I'll talk to you a little bit more about fifth year. Some people probably have heard this idea that we're moving to a kind of a 5-year, a 4 or 5 year model. I'll talk a little bit more about that. So the 4-year program, again, there's a lot of emphasis on design and innovation, working together in teams, because most engineers in the real world and companies work as part of a team, so that's an important skill to acquire. Another thing that you will do is, in fourth year in particular and fifth year, you would work on a solo project, so that's where you kind of have responsibility overall from start to finish in the project. Especially if people do opt for a fifth year, the project becomes quite substantial then. It's quite a significant piece of work. But this is a great thing then to be able to talk to potential employers about, for example. An employer, you go and see some employer, they ask you what you did, what you get in your exams. Well, what you got in your exams, you might have done really well. That doesn't necessarily mean you're actually going to be any use in the real world. But somebody who's done a very good project and understood the challenges, overcame some obstacles, and can talk about that in a job interview, for example, that's an important feature of those kind of interviews. So doing a major project is an important thing. So as I say, typically engineering in Trinity has been 4 years. For a lot of universities, I think it's still 4 years. However, for most of the rest of the world, it's 5 years, and it has been for a long time, particularly in Europe. And as a result of that, Engineers Ireland, which are the kind of oversight body for engineering in Ireland, have feared that, Irish engineers might not be up to the international standard. And the world is, a smaller place all the time. So we are in competition with people from other countries now, particularly within the EU. I mean, somebody can hire an Italian engineer if they want. Doesn't have to get a visa. So Irish engineers, there's a fear that people needed to be competitive at the level of the Europeans. So Trinity have responded to this by offering a fifth year. It's an optional year. Essentially, you can do the 4 years and leave with a bachelor's degree. You can stay for the fifth and get a master's, the equivalent of a master's degree. A couple of issues with this. One is that if you do opt for the fifth year, you have to pay for it, because it is technically a postgrad for 1 year. So there are some fees involved, not for the first 4 years. The other reasons we've responded to this is not just to be competitive with our European counterparts. It's also that the course, engineering is involved. There's a lot of fundamental stuff to learn, and we want to give people then the opportunity to deploy this fundamental learning in projects and so on and so forth. So the schedule basically over a 4 year thing is pretty packed. And the addition of a fifth year allows us a bit more breathing room to develop the course, give a bit more flexibility to students about which projects they might do in a particular semester. Gives you a chance maybe to go outside the college to spend some time abroad. I'll talk to you about that, and come back in. And then gives you a much better chance in fifth year to really do a proper, decent-sized project, which again equips you much, much better when you actually go out into the working world. So in terms of going away, this 5 year program gives us more flexibility in that regard. So we've recently become a partner in this consortium called Unitech, which is a consortium between universities and major international companies. And so the idea of this program is that some students throughout their 5 year will get the opportunity to leave essentially for a year, an academic year, and do half of that academic year in one of these companies, for example, Siemens or Sony or IBM, and then do the second half of that year in one of these international universities. So this gives you a really great exposure because you get a kind of effectively a, you know, international quality internship, and also some exposure to kind of European engineering and what differences there might be in some other university. And then you get to come back and continue on your program here. We're also involved in another European collaboration, which, you know, again, it's just more an academic thing where it's like an Erasmus Mundus style. I think the name of that has changed. Anyway, it's an international opportunity, again, to go away for a semester just to a university. So this doesn't involve a company. But again, it would give you exposure to a broader view of the world and some engineering from a different angle. We're encouraging up to nearly a third of our students to actually try this as part of the 5-year program. So that I've done that slide already. So I'll talk to you a little bit more now, just moving away from electronics and computer engineering specifically. They are areas, I'm a member of the electronic engineering department, so I am an electronic engineer and particularly interested. But in terms of my own research work, I would also class myself as a biomedical engineer. So I'm a member of I'm assistant professor in the School of Engineering, but I'm also what we call a principal investigator, which is basically a scientist in the Centre for Bioengineering. Trinity has a Centre for Bioengineering, which is the leader in bioengineering in Ireland. And I'm also a principal investigator in the Institute of Neuroscience, which is in this building. So I'm particularly interested in brains, and brains work with electrical signals. I'm an electronic engineer. What can I do with these electrical signals from the brain that might be useful to solve problems? How, as an engineer, can I understand more about the brain and their electrical signals, things like that. So I'll show you a few examples of the kind of stuff I might do. And just to highlight, oh yeah, the reason I'm talking about biomedical engineering is because traditionally Trinity has offered mechanical, civil, electronic and computers or computers as specialized streams after third year. But the latest news from the school is that we're going to start a new stream, a biomedical engineering stream. And this will have input from both mechanical and electronic engineering. And I'll show you some examples of the kind of thing a biomedical engineer might do that bring electronics and mechanics into play. So if you were to come to Trinity to engineering next year, you would be eligible to do biomedical engineering by the time you got to third year. So biomedical engineering really is an overlap between engineering and medicine. A lot of mechanical engineers would go in. Someone who wants to design a new artificial hip that's better than the previous one. Someone who wants to design a new, prosthetic arm or something would be a mechanical side of things, where an electronic engineer might design it. I'll talk to you about what they might design here. So here's a couple of examples of electrical signals. Again, the brain operates primarily using electricity, chemicals and electricity. The picture up in the top there is of a young baby who's born prematurely. One of the sad things about some of these babies is that because they're born so early, they're often prone to epileptic fits. But because they're so small, they don't actually manifest physical movement as part of the epileptic fit, so they can be lying there looking peacefully relaxed, and they're actually having epileptic fits that can cause some damage. So one area of research that one of my colleagues is involved in is actually putting electrodes, you just like sticking plaster, you stick them on the head, and these record the electrical activity of the brain, allow the doctors to actually detect these epileptic fits and intervene and help these babies. So that's one example. Another thing that an electronic engineer might do in the biomedical sphere, and some of our colleagues, we have some close contacts with some colleagues in Sydney, Australia, who are the world leaders in this area. So we have quite a close link with those guys, which is great because I'm hoping they're going to send me over there for next winter to do a bit of lecturing, and I'll get the summer down there when it's winter back here. The idea is a lot of people go blind, and blindness is a terrible thing. One type of blindness called retinitis pigmentosa affects the cells in the back of your eye on your retina. So their optic nerve and their brain are still intact, but their retina is damaged. So the retina is what turns light signals into electrical signals in your brain. So if those cells are damaged, those light signals don't get turned into electricity and don't get sent down the optic nerve. So what could an electronic engineer do about this? And people are doing this as we speak. It still doesn't work perfectly, but they're getting closer every day. You could have a camera on your glasses, for example. That camera can take pictures of the world because your retina can't see it anymore. So it can then transmit those pictures, digital pictures or whatever, through some transmission coil into a chip that's on the eyeball. And that chip connects to an electrode grid that tiles across your retina. And it can send spikes of electrical activity as if your retina was still working, as if your retina was there turning the light into electrical signals. Instead, we're using a camera and we're sending that information to a grid of electrodes that then sends the electrical signals. And then, so the information actually still goes down the optic nerve and people can see, even though their eye is damaged, they're using a camera. this idea actually brings up some ethical issues as well. The future might get a bit crazy in the next 100 years. Because, for example, let's say we got this, over 20 years to actually work perfectly, just as well as a normal eye, because it doesn't work that well right now. But if we did get it in 20 years to work just perfectly, then what's to stop us putting an infrared option in this camera? And so all of a sudden, the people who have this prosthetic eye are actually better than the people who don't. Or putting a zoom lens on that camera, and all of a sudden, you can just touch the thing and you can see in the dark. So this stuff is probably going to happen. Right? So in your lifetime, maybe not mine, but. Okay, so that's an example of what an electronic engineer might do in the biomedical sphere. So some of the colleagues that I work with in Sydney are working on this stuff. Some of my own work I won't talk about. I put this slide up a long time ago. This was a kind of a mathematical model I did of retinal cells and how they fire electrical signals, but it's a bit too detailed to go into. This is a massive area of research right now, and an incredibly interesting issue is this thing called deep brain stimulation. People are familiar with Parkinson's disease. I should have brought a video of this because it's so amazing how it works, but I would encourage you, if you're interested, to look up deep brain stimulation Parkinson's on YouTube. It is quite incredible. Parkinson's disease results a lot of times in tremors and movement that people can't control, and sometimes their quality of life is badly affected and they can't really function as they used to. So back in, I think it was the early 90s, there was a French surgeon who happened to be operating on the brain of a patient with Parkinson's. And I'm not clear he had any great idea why he was doing this, but he tried it. He stuck a needle deep in the person's brain and sent in a little electrical pulse. He didn't know necessarily what would happen, so I'm not sure how he explained that to his boss or whatever, but this is what he tried in this patient. And it turned out that this pulse of signals into the deep in the brain made the tremors go away. Right? And so now here we are 20 years later, and people have been doing research on this non-stop ever since, and people still don't know how it works. So it's quite incredible. You will see someone, if you look at the videos, someone who's tremoring very badly with Parkinson's. They have an electrode stuck deep into their brain. They have a little control pad on their chest. And if they turn this on and it starts sending electrical signals, the tremors just go away, and they look absolutely 100% fine. They can walk around. In the States now, they are literally doing deep brain stimulation tests for everything to see if it'll cure anything else magically. I mean, that's as much as we know right now. They're doing it for chronic obesity and overeating. They're doing it for chronic depression. They're doing it for obsessive compulsive disorder. Deep brain stimulation seems to be the answer to a lot of these issues. People still don't know how it works, and electronic engineers, biomedical engineers have a large role to play in trying to figure out how it does work, and also designing better deep brain stimulation kits. So that's, I mean, YouTube will show you an example. It's really amazing. So this is kind of the work that I would do most often, is actually recording data from the head. I don't stick electrodes into people's brains. We just record electrical activity from the head, and we can diagnose some brain conditions. We can do various things. But as an engineer, I'm interested in what can I use this brain activity to do? What can I solve? What problem can I solve with this brain activity and my kind of skill set? So you guys, somebody may have seen this movie. It was out a couple of years ago, maybe not. The idea of this movie was about this book, which was written by a man called Jean-Dominique Bauby, who was a very successful man. He was the editor of a major fashion magazine in France, and he had a massive stroke that left him completely paralyzed. So paralyzed that nobody knew, was he actually still okay, or was he in a vegetative state, or was he still conscious and able to understand what people were saying to him? After some time, people realized that his left eyelid seemed to be flickering, and they realized that he still had some muscle control of his left eyelid and nothing else. So he was trying to communicate just with his left eyelid. So what happened was a nurse would come in to him every day and show letters to him. And when she got to the letter that he was interested in spelling, he would blink the eyelid, and he managed to blink out an entire book about his experience. And despite how depressing it sounds to be locked in like this, what we call a locked-in patient, the book is actually quite uplifting, and without meaning to be too funny about it, it's not a terribly long book, because obviously he had to blink it out one letter at a time. But the sad part of it is that after he blinked this thing out, unfortunately he died before it got published, and he never got to see that it had a huge impact. Lots of people have read it, and they made a movie of it. But if we had some technology, which we do have, because we've got digital cameras, we've got electrodes that we could stick on that would detect the muscle movement in the eye, we could have hooked him up with some brain computer interface, some interface with a computer that would have actually been able to let him spell much, much quicker. He would have got the book written in half the time. So that was something that I got interested in a few years ago. Another example, and I'll show you a cool video of this in a minute, but similar to that issue of paralysis, somebody who loses, breaks their neck or their back can damage their spinal cord. And electrical information goes from your brain to control your muscles. So for example, my right motor cortex here controls my left arm movement. But if I have a spinal break around my neck, then that signal just can't make it to my arm anymore, so I'm paralyzed. The signals just can't make it. So what happens, much as with the retina thing I showed you a minute ago, what happens if we have some sensory input that we can pick up from the brain signals, we can pick up some brain activity, can we just skip the spinal cord and just send electrical stimulation to the arm directly if we know what these signals mean, rather than let it have to go down through the spinal cord because we use a computer instead, for example? I'll skip this one because I have a video of this later on. So this is something that I was interested in doing. Firstly, this was a thing I did with the MIT lab that I worked in for a while. We created a video game that you could control just using your brain activity. So you didn't have to move at all. This character was walking across a tightrope, was going to fall left or right. And just using the signals that were on your brain, we were able to flash these yellow dot stimuli on the screen here. Just by using frequencies of these different yellow dot stimuli on the person's brain activity, we could tell which way they wanted this guy to fall, and he could balance and work across the tightrope. So this would have been a great thing for Jean-Dominique Bauby to have, some direct interface where he didn't have to move, but he could still communicate directly from his brain. Now, it doesn't work 100%, but it works pretty well. And this is this idea of the spinal cord injury. Can we just, we've got a break in the spinal cord. Can we take information from the brain, interpret it, and just bypass the spinal cord? Let's let the brain signals directly control the environment. So here's a chap who unfortunately is paralyzed, and he's trained, I don't know how, I don't work a Mac. All right, here we go. This guy unfortunately, come on. Sorry about that, I should have used my own computer. So the idea of this is that this guy is controlling, we collect brain signals from his scalp, and we can interpret. He is trained for now. He will have trained for several weeks to get good at this, but he has trained such that he can generate various different electrical signals on his scalp, and we can pick them up. And those signals can be interpreted by the computer, which is on the back of the wheelchair, and he can drive around. He can actually control his own wheelchair, even though he has no muscle movement from his neck down. So, yeah, sometimes it's still a ways away in the future, but at the moment, with people who are very badly paralyzed, we're actually starting to interface electronics with actual neural tissue, so people are actually starting to put electrodes into human brains to actually interpret the signals a bit better. There's challenges in this area in terms of materials, electronic materials and stuff like that, that the brain doesn't like stuff stuck in it. So, but in the future, people are working towards materials that you could mesh electronics with brains, and would be, I don't know, what would be half human, half robot, I don't know. But here's another video. Hopefully this one will work. Do you know how to do this? Play my video? I don't know how to work a Mac.
Which one is it?
That one would work if you can play that. Okay, so this lady has lost her arm, but she still has obviously shoulder muscles and chest muscles and stuff. So by putting electrodes on her shoulder and chest, and by letting her practice for a while, we can start to interpret what these signals are that are coming off her shoulder and her chest muscles. And we can then transmit those signals using electronics to some mechanical operators in this fake arm that she has, this prosthetic arm. And that has allowed her quite good control. She can move and reach and pick things up just based on the electrical signals that she's generating around her shoulder and her arm. So this would be a kind of a half electronic, half mechanical project in the bioengineering domain. So I just wanted to show you that, because as an electronic engineer, but also a bioengineer, and with this new bioengineering stream coming on board, I wanted to show you guys what that entailed. All right. Yeah, pity I can't show you the guy in the wheelchair, but you'll just have to take it from me that it works. I don't know how to do this. I'm going to have a go. Play from current. There we go. So anyway, yeah, I'll just wrap up, because I think I've gone over time. So my own interest is biomedical engineering from an electronic perspective. Electrical machines are a big thing for the future. Electric cars, robots, industrial machines, power systems, energy crisis, getting electricity that we all use and love so much. How are we going to do that better in the future? Microelectronic circuits. Anyone who's got a smartphone's got a lot of microelectronic circuits in their pocket right now. That's not going anywhere anytime soon. Computers and the internet aren't going away. Communications, electronic communications aren't going anywhere. So electronic engineering is important and for the future. All right. Anyone got any questions before? If you want to, you can just come down. I'll hang here for a few minutes and you can ask me some questions if you want to. All right.